The future is arriving. Imagine a world where humanity is no longer confined to Earth, where space is not a distant frontier, but a domain we navigate, inhabit, and even reshape. For centuries, we looked up at the stars and wondered what lay beyond, dreaming of distant worlds while our feet remained on a single planet. Now, advances in physics, engineering, and technology suggest that we are on the cusp of a new era where humans become a multi-planet species traveling farther, faster, and with possibilities we never thought possible. Today, I want to take you on a journey through the next era of space exploration, exploring how science is transforming dreams into reality, and what this means for humanity as future that the moon has always held a unique place in human imagination. For centuries, it was a distant, unchanging celestial body, a symbol of mystery and curiosity. Its surface forever etched with craters and shadows. The Apollo missions brought humanity to its surface, but those landings were brief, fleeting moments in time. They were spectacular, yes, but they left the moon largely untouched, a place that was observed more than inhabited. Today, the perspective has shifted dramatically. The moon is no longer simply a destination for symbolic achievement. It is the first stepping stone in humanity as journey to becoming a multiplanetary species. Lunar colonies are envisioned not as temporary outposts but as self-sustaining habitats, laboratories for testing life support systems, and strategic bases from which humans can develop the technologies needed for survival in space. The moon's gravity, about 1/6 of Earth, provides an environment where structures and spacecraft can be tested in reduced gravity, preparing for longer-term habitation on planets like Mars. Its surface contains valuable resources, such as helium-3, a potential fuel for fusion energy, and water ice, which can be converted into oxygen and hydrogen for life support and rocket fuel. The moon thus represents both a laboratory and a resource hub, a practical proving ground for technologies that will enable humanity to move farther into the solar system. Establishing colonies on the moon is not simply an engineering challenge, it is a holistic undertaking that combines biology, ecology, architecture, and social science. Humans cannot survive long on the lunar surface without protective habitats that shield against extreme temperature fluctuations, cosmic radiation, and micrometeorite impacts. These habitats must be self-sustaining, incorporating systems for water recycling, air purification, food production, and energy management. Each system must be reliable, resilient, and adaptable because the moon offers no quick rescue if something fails. Beyond the technical considerations, there's the psychological challenge. Living in a confined, isolated environment for extended periods of time requires careful attention to mental health, social dynamics, and human behavior. Astronauts must be prepared for extended periods without direct contact with Earth, learning to cooperate and thrive in an alien environment. In this way, lunar colonies serve not just as technological testbeds, but as training grounds for the human mind, teaching resilience, adaptability, and the social skills necessary for life beyond a single world. The strategic importance of the moon extends beyond its immediate role as a habitat or resource source. Its position relative to Earth makes it an ideal location for astronomical observation and experimentation. Telescopes placed on the far side of the moon, shielded from Earth's radio interference, could provide unprecedented clarity for observing the cosmos, from distant galaxies to subtle cosmic background radiation. The moon could serve as a staging area for missions deeper into the solar system, allowing spacecraft to refuel, gather supplies, and undergo final system checks before departing for Mars, asteroids, or beyond. By establishing a permanent presence on the moon, humanity gains both a practical base for expansion and a platform for scientific discovery. The lessons learned on the lunar surface will directly inform the design of habitats, life support systems, and exploration strategies for planets farther afield, making the moon an indispensable first step in the broader vision of interplanetary civilization. Mars represents the next frontier in humanity's journey beyond Earth, a word that has fascinated scientists, writers, and explorers for centuries. Unlike the Moon, which is a near neighbor and relatively static in its challenges, Mars is a planet with a thin atmosphere, surface gravity about a third of Earth's, and a climate that oscillates between extremes of cold and occasional warmth. Colonizing Mars presents a host of challenges that require technological innovation and human ingenuity. The thin atmosphere provides minimal protection from cosmic and solar radiation, necessitating the development of shielding technologies and underground or heavily insulated habitats. Water is scarce and primarily locked in ice at the poles or beneath the surface, meaning that in situ resource utilization, extracting water from the soil and atmosphere, will be essential for sustaining life. Food production on Mars will require controlled agricultural systems capable of operating in reduced gravity and low light conditions. Each of these challenges forces us to rethink how humans live, work, and survive, transforming Mars into a living laboratory for human adaptation in extraterrestrial environments. Human missions to Mars are also opportunities to advance propulsion and transportation technologies. Traditional chemical rockets are capable of reaching Mars, but the journey takes months and exposes astronauts to prolonged microgravity and cosmic radiation. Advanced propulsion systems, including nuclear thermal rockets, ion drives, and potentially fusion-based engines, could shorten travel times and reduce risk, making round-trip missions more feasible and sustainable. In addition to propulsion, landing and takeoff present significant engineering challenges. Mars' thin atmosphere makes aerodynamic braking less effective, requiring innovative solutions such as supersonic retropropulsion or inflatable deceleration devices. Each step of planning, from Earth launch to Mars landing, is an exercise in applied physics and engineering, forcing humans to master the complexities of interplanetary travel. Colonizing Mars is not simply a matter of technology, it is also a profound social and psychological experiment. Humans living on Mars must operate in isolated, confined communities, often cut off from immediate support from Earth. Cooperation, trust, and communication become vital for survival. Missions must be designed with redundancy, resilience, and contingency planning, ensuring that life support systems, energy grids, and habitats can withstand failures or unexpected events. Over time, these Martian colonies may develop their own culture, norms, and social structures, reflecting the unique environment and challenges of life on another planet. The process of adapting to Mars will teach humanity invaluable lessons about living in extreme conditions, planning for long-term survival, and maintaining social cohesion in confined, high-stakes environments. In many ways, the psychological, social, and technological insights gained from Mars will pave the way for more distant exploration, helping humans prepare for life on moons of Jupiter, Saturn, and eventually exoplanets beyond our solar system. Mars also offers an unparalleled opportunity for scientific discovery. Its surface preserves a record of billions of years of planetary history, including evidence of water, volcanic activity, and potentially even ancient life. Robotic missions have revealed riverbeds, minerals, and ice deposits, but humans have the ability to explore more comprehensively, conduct complex experiments, and adapt in real time to unexpected discoveries. The search for microbial life, signs of past ecosystems, or unique geological formations could fundamentally change our understanding of biology, evolution, and the history of the solar system. In addition, learning to live on Mars allows scientists to test new technologies for terraforming, resource utilization, and ecological management, building the foundation for even more ambitious endeavors, including interstellar travel. Mars is both a challenge and a classroom, a place where humans confront the harsh realities of another world while simultaneously expanding knowledge, capability, and imagination. Finally, both the Moon and Mars represent more than technological or scientific challenges. They symbolize a transformation in human perspective. For centuries, we have been confined to our planet, bound by gravity, atmosphere, and our own limited reach. Establishing colonies on these celestial neighbors forces us to think beyond Earth, to consider long-term sustainability, interplanetary logistics, and the social and psychological needs of humans living in extreme conditions. The lessons learned from these endeavors are not limited to space. They feed back into life on Earth, inspiring innovations in energy, resource management, habitat design, and international collaboration. The next era of space exploration begins here, with lunar and Martian colonies as laboratories, proving grounds, and harbingers of a future in which humanity is no longer tied to a single world. The Moon and Mars are stepping stones to the stars, and every challenge we overcome on these worlds brings us closer to becoming a civilization that thrives across the solar system and eventually beyond. The vastness of space holds not only the promise of new worlds, but also the potential of untapped resources that could transform humanity's future. Among the most promising of these opportunities is asteroid mining, a concept that may seem like science fiction but is firmly grounded in physics, economics, and engineering. Asteroids are rich in metals such as platinum, nickel, iron, and rare earth elements, as well as water and other volatiles essential for sustaining life and propulsion in space. The ability to extract these resources represents a paradigm shift in how humanity approaches expansion into the cosmos. No longer must we rely solely on Earth for raw materials. The universe itself becomes a repository of wealth and energy, a source of sustenance for interplanetary and eventually interstellar exploration. These celestial bodies, which for millennia were nothing more than points of light moving across the night sky, are now understood as tangible assets waiting to be harvested with precision technology and careful planning. The science and engineering behind asteroid mining are both fascinating and complex. Robotic probes must be capable of intercepting, anchoring to, and extracting materials from bodies that move at high velocities and have negligible gravity. Unlike mining on Earth, where gravity and atmosphere provide stability, asteroids present microgravity environments in which every action has a reaction, and even small mistakes could send a spacecraft tumbling into an uncontrollable spin. Solutions require advanced robotics, autonomous systems, and real-time feedback mechanisms to stabilize the equipment, extract material, and transport it back to collection or processing stations. The technology developed for asteroid mining would not only unlock resources but also advance our understanding of space operations, robotics, and remote systems control. In this way, asteroid mining is both a practical enterprise and a driver of innovation, creating tools and expertise that are essential for the next era of human exploration. Beyond the technological challenges, asteroid mining introduces profound economic and strategic implications. Space becomes not merely a domain of exploration, but a realm of production and trade. Water extracted from asteroids can be converted into fuel, enabling spacecraft to refuel in orbit, extend mission duration, and explore further without returning to Earth. Metals and rare elements can support construction of space habitats, manufacturing of advanced electronics, and development of new propulsion technologies. In this context, the solar system itself becomes a resource economy, reducing dependence on Earth and enabling a sustainable, scalable model for interplanetary expansion. This also raises new ethical and legal considerations, as humanity must develop frameworks for the ownership, management, and fair use of extraterrestrial resources. These are challenges not only of science and engineering, but of policy, governance, and philosophy, forcing us to consider what it means to responsibly utilize the cosmos. Space habitats represent the next step in humanity's transition from planetary to interplanetary civilization. While lunar bases and Martian colonies provide foundational experience, artificial space habitats allow for living environments independent of planetary surfaces, opening entirely new possibilities for population growth, experimentation, and sustainability. These habitats, often envisioned as large rotating cylinders or spheres, simulate gravity through centrifugal force, enabling humans to maintain health and comfort over long duration. Within these structures, entire ecosystems can be developed, incorporating water cycles, agriculture, and energy systems that support life in a closed environment. The design and construction of space habitats is a multidisciplinary challenge requiring mastery of physics, engineering, biology, and social science. Every decision, from structural materials to life support systems, must be made with both precision and adaptability, because failure is not an option when survival depends on the artificial environment. Artificial space habitats are not simply about survival. They offer an unparalleled opportunity for experimentation and innovation. Scientists can study human behavior, social dynamics, and ecological systems in environments that are isolated and self-contained, providing insights into everything from long-duration psychological health to closed-loop agricultural systems. These habitats can serve as laboratories for developing the technology and social organization required for even more distant colonization, including missions to outer planets, moons, and potentially interstellar destinations. Moreover, they allow for the testing of advanced propulsion systems, energy harvesting technologies, and artificial intelligence in conditions that simulate the extremes of space travel. In this way, space habitats function as both living environments and research platforms, accelerating humanity. Understanding of how to survive, adapt, and thrive beyond Earth. The engineering challenges of space habitats are staggering yet inspiring. Rotational design for artificial gravity must balance centripetal force with structural integrity, requiring precise calculations and materials capable of withstanding stress over decades. Radiation shielding is essential, as cosmic rays and solar radiation pose significant health risks. Solutions range from layers of water, regolith, or specialized composites, each with advantages and trade-offs. Life support systems must maintain air, water, and food cycles indefinitely, demanding redundancy, monitoring, and automated feedback to ensure stability. Energy systems, potentially based on solar power or nuclear fusion, must provide continuous, reliable supply for all aspects of life, from habitation to scientific research. These requirements create a nexus of innovation, where advances in one field, material science, robotics, or energy, directly enable progress in others. The cumulative effect is a leap forward in human capability, providing the foundation for a civilization that can function independently of any planetary surface. Social organization within space habitats is as critical as technological innovation. Humans are social creatures, and long-term habitation in confined environments presents challenges to mental health, cooperation, and governance. Psychological resilience, conflict resolution, and community management become as important as oxygen and water. Habitats provide the opportunity to design new forms of social systems that can withstand isolation, high stakes, and long duration. Communities can experiment with collaborative decision-making, education, governance, and culture in ways impossible on Earth, creating models for life in the vast, interconnected expanse of space. These lessons will be essential as humanity expands, ensuring that technological capability is matched by social resilience and adaptability. Artificial habitats also redefine the concept of home. Humans no longer need to be bound to the surface of a planet. They can live and thrive in orbit in interplanetary space, or near resource-rich asteroids. This flexibility expands the frontier of human civilization, allowing settlements to exist where resources are abundant, missions are strategically advantageous, and scientific exploration can be maximized. The ability to live independently of planetary surfaces also mitigates risk, providing redundancy for the survival of the species in the face of global catastrophes on Earth. In essence, space habitats transform the universe itself into a canvas for human ingenuity, creativity, and exploration, turning the vast emptiness of space into environments capable of sustaining life and advancing civilization. The combination of asteroid mining and artificial space habitats represents a synergy that propels humanity into a new era. Resources extracted from asteroids can support the construction, maintenance, and expansion of habitats, while habitats provide the infrastructure and human presence necessary to manage and utilize these resources efficiently. This integrated approach transforms space from a distant frontier into a domain of practical opportunity where survival, exploration, and economic activity intersect. Together, asteroid mining and space habitats create the foundation for an interplanetary civilization, enabling humans to expand beyond a single world, learn to live sustainably in extreme conditions, and prepare for the even greater challenges of interstellar exploration. The next era of space exploration is defined by this integration of technology, ingenuity, and vision of future where humans do not merely visit space, but inhabit, utilize, and thrive within it, turning the cosmos itself into a stage for human innovation and growth. The vast distances of space have always been one of the greatest barriers to human exploration, and overcoming them requires not just ambition, but revolutionary advances in propulsion technology. Traditional chemical rockets, while powerful, are limited by the amount of fuel they can carry and the energy density of chemical reactions. For interplanetary missions, these methods are sufficient, though still slow, taking months to reach Mars or years to travel to the outer planets. However, if humanity is to consider truly expansive exploration reaching distant asteroids, the moons of Jupiter and Saturn, or even the nearest star systems, new propulsion concepts are essential. Innovations such as ion drives, nuclear thermal rockets, fusion engines, and even animated propulsion offer the potential to reduce travel time dramatically while increasing efficiency and payload capacity. Each of these technologies is grounded in well-established principles of physics, yet each requires extraordinary engineering, ingenuity, material science, and energy management. Ion drives, for example, operate with incredible efficiency over long durations, providing small but continuous thrust that accumulates into impressive velocity over time. Nuclear thermal rockets harness the energy of nuclear reactions to heat propellant directly, offering far higher thrust and efficiency than chemical rockets. Fusion engines, while still largely theoretical, promise to release energy on a scale comparable to the Sun, propelling spacecraft at unprecedented speeds. Antimatter propulsion, one of the most speculative yet physically consistent concepts, could provide nearly unmatched energy density, enabling acceleration over light years in timescales accessible to human lifetimes. These concepts collectively redefine what is possible in interplanetary and eventually interstellar travel, shifting the constraints from mere distance to technological mastery. The development of these advanced propulsion systems is not merely an academic exercise, it fundamentally alters humanity as approach to space exploration. Faster, more efficient engines make it feasible to send larger payloads, including humans, equipment, and habitats, to distant destinations. They reduce the exposure of astronauts to cosmic radiation and microgravity by shortening travel times, thereby increasing the safety and feasibility of manned missions. Moreover, advanced propulsion enables more ambitious mission planning, simultaneous exploration of multiple destinations, orbital infrastructure deployment, and rapid response to newly discovered phenomena in space. These technologies are also synergistic with other areas of space exploration, including asteroid mining, planetary colonization, and orbital habitats. For example, a fusion-powered spacecraft could transport mined materials from an asteroid belt to a lunar or Martian colony, providing essential resources while demonstrating the practical utility of advanced propulsion. The implications extend beyond technology. They redefine logistics, economics, and the strategic potential of human civilization in space. Equally critical to the next era of space exploration is the integration of robotics and artificial intelligence into every aspect of mission planning and execution. While humans bring creativity, intuition, and adaptability, robots and AI can operate continuously with precision and resilience in environments that are hostile or inaccessible. Autonomous spacecraft can navigate complex gravitational fields, dock with orbiting stations, or conduct high-risk asteroid mining operations with minimal human intervention. AI systems can monitor life support systems, predict mechanical failures, and optimize energy usage in real time, ensuring that human crews remain safe and productive. Furthermore, robotics allows exploration of extreme environments that humans cannot yet reach safely, the high-pressure oceans of Europa, the icy crust of Enceladus, or the radiation-drenched surface of Jupiter's moons. Through the combined use of AI and robotics, humanity can extend its reach beyond immediate physical limitations, conducting scientific observation, construction, and resource extraction across the solar system with unprecedented efficiency. The collaboration between humans and AI also redefines the role of decision-making in space. In environments where communications with Earth may be delayed by minutes or hours, autonomous systems must make split-second decisions to adjust trajectory, manage resources, or respond to emergencies. Machine learning algorithms trained on vast datasets of space missions and simulations can detect subtle patterns, anticipate hazards, and provide recommendations to human operators. This creates a symbiotic relationship where human judgment is enhanced by computational power, and AI systems benefit from human creativity and oversight. Such collaboration not only ensures mission success, but accelerates the development of new technologies, operational protocols, and strategies for long-duration space exploration. The result is a feedback loop of innovation, where each mission informs the next, continually improving efficiency, safety, and scope. The implications of robotics and AI extend beyond operational efficiency. They transform the economics of space exploration by reducing costs, increasing scalability, and allowing for continuous operation without the constraints of human fatigue or life support requirements. Robotic systems can assemble structures in orbit, construct habitats, and even manufacture components using in-situ resources, turning distant worlds into functional infrastructure hubs. They also allow humans to focus on high-value tasks, scientific analysis, decision-making, and creative problem solving while delegating repetitive, hazardous, or complex operations to machines. This synergy between humans and AI enables a level of productivity in space that is comparable to or even exceeds that of terrestrial industries, paving the way for sustainable, scalable human presence beyond Earth. Beyond the practical, the use of robotics and AI carries profound philosophical and cultural implications. It challenges the traditional boundary between human and machine, between manual exploration and autonomous operation. Humans will become managers, collaborators, and interpreters of data collected by sophisticated systems that can operate independently across the solar system. This partnership raises questions about responsibility, control, and the nature of intelligence as humans extend their consciousness into machines that act on their behalf. It also amplifies human potential, allowing civilization to reach farther, observe more comprehensively, and adapt more quickly than ever before. By integrating robotics and AI with advanced propulsion, humanity gains not only the ability to explore, but also the capacity to manage, understand, and thrive in a complex, dynamic cosmic environment. Together, advanced propulsion and intelligent robotics represent a convergence of innovation that propels humanity into a new era of space exploration. The ability to move quickly and efficiently across the solar system, combined with the capacity to operate safely and autonomously in hazardous environments, transforms distant planets, moons, and asteroids into accessible, manageable domains. It shifts exploration from a linear, sequential process into a multidimensional network of operations where multiple missions, destinations, and objectives can be pursued simultaneously. This era requires not only mastery of physics and engineering, but also a new way of thinking about civilization itself, how humans interact with machines, how societies coordinate complex projects across space, and how knowledge, resources, and decision-making are integrated on cosmic scales. Advanced propulsion and AI together redefine the boundaries of possibility, demonstrating that the next era of space exploration is not limited by distance, danger, or duration, but by imagination, vision, and the willingness to turn theory into practice. The search for life beyond Earth is one of the most profound and compelling drivers of space exploration. For centuries, humans have gazed at the stars and wondered if we are alone, But only recently has technology allowed us to begin answering this question with scientific rigor. From the frozen oceans of Europa to the methane-rich atmosphere of Titan, the moons of our solar system present environments where life, if it exists, could survive and even thrive. Microbial life, simple and hardy, may cling to subterranean oceans, protected from radiation and extreme temperatures, offering a window into forms of life entirely alien to our own. Beyond our solar system, exoplanets orbiting distant stars offer another tantalizing possibility. Worlds with the right combination of temperature, water, and chemical elements that could support life as we know it, or even life as we do not yet imagine. Each discovery, whether of an organic molecule, a biosignature gas, or a geological formation suggestive of biological processes, transforms the search for life from speculation into a concrete scientific endeavor. The implications of discovering even the simplest life form beyond Earth are enormous. It would revolutionize biology, forcing us to reconsider the universality of life's processes and the diversity of evolutionary pathways. It would alter philosophy, challenging humanity's perception of uniqueness and place in the cosmos. And it would reshape culture, inspiring art, literature, and a collective sense of wonder that extends beyond our planetary boundaries. The search for life is thus not only a scientific quest, but a profound journey of human self-discovery, revealing what it means to exist in a universe that may be teeming with possibilities we have yet to comprehend. The methodology for searching for life is as fascinating as the quest itself. Robotic probes are the first explorers equipped with spectrometers, cameras, and drills to examine surfaces and atmospheres for chemical imbalances, water, or organic compounds. Missions to Mars, such as the rovers Perseverance and Curiosity, have already provided tantalizing evidence of ancient riverbeds and mineral deposits formed in the presence of water, suggesting that the planet may once have harbored conditions suitable for life. Future missions aim to collect samples, analyze isotopic ratios, and search for biomarkers, chemical fingerprints indicative of past or present life. In the outer solar system, probes targeting icy moons are designed to penetrate subsurface oceans, melt through kilometers of ice, and analyze the liquid water beneath for microbial life. Beyond the solar system, telescopes equipped with advanced spectroscopy will examine exoplanet atmospheres for gases like oxygen, methane, or carbon dioxide in unusual proportions, which may signal biological activity. These methods represent a combination of precision engineering, computational analysis, and imaginative science, each designed to push the limits of what is observable and knowable about distant worlds. The discovery of life, or even the potential for life, has profound implications for humanity's exploration priorities and societal perspective. If microbial life is found on Europa, Enceladus, or Mars, it confirms that life is not unique to Earth, suggesting that the universe may be far more biologically active than previously imagined. This would prompt a re-evaluation of exploration strategies, emphasizing the protection of extraterrestrial ecosystems, the study of astrobiology, and the ethical considerations of human interaction with alien life. Such discoveries would influence the design of habitats, planetary protection protocols, and mission planning, ensuring that humanity explores responsibly, preserving life forms that may hold insights into biology, evolution, and even the origins of life itself. Philosophically, the confirmation of life elsewhere expands our sense of connection to the cosmos, challenging anthropocentric views and inspiring a broader, more inclusive vision of life's place in the universe. Beyond the scientific and philosophical dimensions, the search for life also drives technological innovation. Detecting microbial life requires instruments of extraordinary sensitivity, capable of distinguishing between biological and non-biological signals in extreme environments. Autonomous exploration, precision navigation, and remote sensing technologies are continually refined to meet these challenges, often yielding breakthroughs that extend to Earth-based applications. For example, advances in robotics, artificial intelligence, and analytical instrumentation for space exploration, enhanced medical diagnostics, environmental monitoring, and industrial automation on our own planet. The quest to find life elsewhere thus has a dual effect. It expands our scientific horizons while simultaneously driving technological progress that benefits society in countless tangible ways. The ultimate vision, however, lies in humanity becoming a multiplanetary species. Colonization of other planets, moons, and orbital habitats ensures that humanity is not constrained by the fragility of a single world. Life beyond Earth provides a safeguard against extinction, allowing human civilization to survive potential planetary catastrophes such as asteroid impacts, climate upheaval, or other unforeseen disasters. More than survival, multiplanetary habitation encourages cultural, intellectual, and technological evolution on unprecedented scales. Each new settlement becomes a laboratory of human adaptation, testing new forms of governance, education, social cohesion, and technological integration. Populations spread across diverse environments cultivate resilience, creativity, and innovation, enabling humanity to thrive in conditions that challenge our current limitations. This expansion is not merely physical, it is a cognitive and societal evolution, pushing humans to think, plan, and act on interplanetary scales. Becoming a multiplanetary species also fundamentally changes the way humanity views itself and its place in the cosmos. On Earth, civilizations have always been bounded by geography, political borders, and natural resources. Beyond Earth, these limitations dissolve, replaced by the vast canvas of space, where cooperation, ingenuity, and foresight are essential for survival and progress. Interplanetary civilization requires the integration of technology, governance, and culture in ways unprecedented in human history. Energy management, resource allocation, and habitat construction become interdependent systems that span multiple worlds. Communication and decision-making must overcome light-year delays and isolated outposts, requiring autonomous systems, artificial intelligence, and highly coordinated human collaboration. In essence, humanity is challenged to grow in complexity and capability, learning to operate as a single species across planetary and eventually interstellar distances. Furthermore, the endeavor of becoming multiplanetary fosters profound philosophical and cultural transformation. Humanity is forced to confront questions of identity, ethics, and purpose in the context of the universe. What does it mean to be human when our descendants may live on Mars, orbiting habitats, or distant exoplanets? How do we balance exploration with preservation, ambition with responsibility, and curiosity with ethical stewardship? These questions shape not only policy and technology, but also the stories, art, and collective consciousness of humanity. Multiplanetary civilization transforms space from a void into a domain of human experience, imagination, and growth, where exploration is intertwined with the evolution of culture, society, and knowledge. Ultimately, the search for life and the pursuit of multiplanetary civilization are intertwined threads of a grand human narrative. Discovering life beyond Earth challenges our understanding of biology, philosophy, and existence, inspiring curiosity and humility in the face of the cosmos. Simultaneously, expanding humanity across planets ensures survival, cultivates resilience, and opens unprecedented opportunities for scientific, technological, and cultural advancement. Together, these twin pursuits, searching for life and becoming a multiplanetary species, define the next era of human space exploration. They push us to innovate, to imagine, and to act boldly, turning distant dreams into tangible realities, and setting the stage for a future where humanity thrives not only on Earth, but among the stars themselves. As we reflect on the incredible possibilities before us, it becomes clear that humanity stands at the threshold of a new era, an era defined by exploration, discovery, and expansion beyond our home planet. From the moon to Mars, from asteroid resources to space habitats, from the search for life to becoming a multiplanetary civilization, each step represents not only a technological achievement, but a transformation in how we understand ourselves and our place in the cosmos. The universe, once distant and untouchable, is becoming a landscape of opportunity, where human ingenuity, courage, and curiosity can thrive on unimaginable scales. Every mission, every experiment, and every discovery is a step toward a future where humanity does not merely survive, but flourishes across worlds, learning, growing, and reaching for the stars. Thank you for joining me on this journey of imagination, knowledge, and cosmic exploration. Your curiosity, passion, and willingness to dream alongside science are what drive us forward, inspiring each generation to reach farther and aim higher. Together, we step boldly into the vast, magnificent universe that awaits us, and the adventure has only just begun.